Hi students, we have already completed the substitution reactions of alkyl halides. I told you that alkyl halides can undergo elimination reactions also. Let us see the elimination reactions. What is meant by elimination reactions? During elimination reactions, an atom or group of atoms are eliminated from the molecule. During elimination reactions, a sigma bond is converted into a pi bond. I will show it for you. This is ethyl bromide. When made to react with alcoholic potassium hydroxide, this hydrogen is being consumed by C2H5O minus. It is consuming proton here, means it is a base. Then the sigma bond is moving here and this sigma bond is going out, CH2 double bond CH2. A new pi bond is formed. Since sigma bond has converted into pi bond, sigma bond is stronger than pi bond. A strong bond is broken and a weak bond is formed, means energy is consumed in the reaction. I am writing energy on the product side, so energy is consumed. So all elimination reactions are endothermic in nature. Since during elimination reactions a sigma bond is broken and a pi bond is formed, a stronger bond is replaced by weaker bond, energy is being consumed, and the reaction is endothermic. So all elimination reactions are endothermic in nature. Now let us see different types of elimination reactions today being given by alkyl halides. Can undergo two types of eliminations, alpha elimination and beta elimination. And alpha elimination also called 1,1 elimination and beta elimination is called 1,2 elimination. In alpha elimination, both the proton and halide ion replaced from the same carbon atom. This is ethyl chloride CH3 CH2Cl. I am using alcoholic potassium hydroxide, mixture of ethyl alcohol and KOH, which provides you C2H5O minus. Now it consumes the proton and Cl minus goes out, which leads to the formation of the so-called CH3, CH2, CH double dot. These are called carbenes. This is ethyl carbene. Now if you take beta elimination, these are very rare. These are this is ethyl carbene. This is an intermediate, reaction intermediate. So it will be further consumed in the reactions. So in beta eliminations, the hydrogen atom, that is the proton and the halogen, are removed from or eliminated from adjacent carbon atoms. This is the alpha carbon, this is the beta carbon. Halogen attached carbon is alpha and the next carbon is beta. Here the hydrogen is or the proton is removed from beta carbon and halide ion is moving like this. As a result, you are getting this product. This is an example of beta elimination. In alpha elimination, both the proton and halogen are removed from the same carbon. In beta elimination or 1,2 elimination, both proton and halogen are removed from adjacent carbon atoms. Now let us see the most important of reactions, beta elimination reactions here. When we take beta elimination reactions, the beta elimination reactions mainly proceeds through two types of mechanisms, mainly what we have in syllabus I am discussing. So that is E2 mechanism, E1 mechanism. E2 mechanism means bimolecular elimination. E1 mechanism means unimolecular elimination. In bimolecular elimination, the rate of the reaction depends upon the alkyl halide and the base. In bimolecular elimination, the rate of the reaction depends upon the concentration of the alkyl halide and concentration of the base, and in even mechanism the rate of the reaction depends upon concentration of the alkyl halide alone. So let us first take up the E2 mechanism and then followed by E1 mechanism. E2 mechanism. In E2 mechanism, rate of the reaction depends upon concentration of the alkyl halide and the base which consumes the so called proton. It is first order with respect to alkyl halide, first order with respect to base. That means the rate law or rate equation suggests that the rate of the reaction is depending on the concentration of the alkyl halide and base. Let us take up an example for that. This is what I have taken. N-propyl bromide is made to react with alcoholic KOH, mixture of ethyl alcohol and KOH. It provides you ethoxide ion. This ethoxide ion removes this is alpha carbon, this is beta carbon, proton from beta carbon, and simultaneously, we are using the word simultaneously Br minus goes out, and both H plus and Br minus are removed simultaneously in single step. So E2 mechanism is similar to SN2 mechanism, is a single step reaction. Here initially, that means it involves a transition state rather than intermediate. So it will initially, when consuming proton, it forms a transition state where C2H5O minus is slowly forming bond with hydrogen. Then the CH bond is weakening. This is forming bond, this is breaking bond. Then this is the sigma bond already existing between the carbons. Now here this bond, Br bond, CBr bond is slowly breaking down. This is breaking down, and here a pi bond is formed. This is forming. This is forming, this is forming, these are breaking down. And this is the transition state which is obtained or formed during the reaction, and the product is CH3, CH, double bond, CH2. If you clearly observe the transition state, it has alkene character, a double bond character, and the alkene is formed due to elimination of HBr. So alkyl halides when treated with alcoholic KOH undergo elimination, beta elimination, to produce alkenes, and this particular mechanism is E2 mechanism. It is formed along with Br minus. Br minus has come out. That means, and it's C2H5O minus consuming H plus, so it is forming alcohol also. So it is eliminating H and Br simultaneously. Simultaneous elimination of H plus and Br minus is taking place in E2 mechanism. Is taking place in E2 mechanism. This is the mechanism for you. Ethoxide ion obtained from alcoholic KOH consuming the proton from beta carbon. Then Br minus is simultaneously going out. So you are getting a transition state which has an alkene character. So now we can say that any alkyl halide which has tendency to form a more stable alkene is a more preferable substrate for the SN2 mechanism. So that's why I can say that tertiary alkyl halide is a better substrate than isopropyl. This is tertiary butyl bromide, this is isopropyl bromide, then ethyl bromide are suitable substrates. Tertiary alkyl halide is preferred over secondary alkyl halide, is preferred over primary alkyl halide for the E2 mechanism. So the favorable alkyl halide is tertiary alkyl halide because it forms a more stable alkene. Tertiary alkyl halide forms more stable alkene than secondary alkyl halide than primary alkyl halide. And one more thing is, what type of halogen is preferred? A better leaving group. Whichever leaves better is important. Then in alkyl halide, the halogen should be a better leaving group. That's why for a given alkyl group, alkyl iodide is better than, alkyl bromide is better than, alkyl iodide is better than alkyl fluoride, because Iodide is a better leaving group than bromide, than chloride, than fluoride. So, as far as alkyl halide is concerned, a tertiary alkyl group with better leaving group is a suitable substrate. What about the base? Base is normally a strong base like ethoxide ion is preferred. I can say suitable base is an ethoxide ion or a strong base, preferably high concentration of strong base. So, the favorable conditions for E2 elimination are an alkyl halide capable of forming a stable alkene with a better leaving group like iodide, and high concentration of strong base is preferred for E2 elimination. This is the mechanism of E2 elimination. Now, let us take up the mechanism of E1 elimination, unimolecular elimination. Mechanism of E1 elimination. E1 elimination is unimolecular elimination. In unimolecular elimination, the rate of the reaction depends on concentration of the alkyl halide and base has no role to play. Now, E1 elimination is a two-step mechanism in which in the first step alkyl halide forms a carbocation. In the second step the carbocation will lose the proton from the beta carbon atom and forms an alkene. Now, I will show that for you. I will consider tertiary alkyl halide and then with water, boil with water, heat with water. I told you that all elimination reactions are endothermic reactions, so that is why it prefers high temperatures. Now, what will happen is in the first step, that is a slow step and RDS, where a carbocation is formed in the slowest step of the reaction. Now, this carbocation loses the proton from beta carbon. Here the solvent itself functions as a base. A weak base is enough for E1 mechanism. So, this will take up this proton and the sigma bond is slowly converting into pi bond in the fast reaction, giving you CH2 double bond C CH3 CH3. So, it is very clear that in the first step, that is in the slowest step, a carbocation is formed. When a tertiary alkyl halide is boiled with water, water is functioning as a base also, solvent as well as base. So, it is helping to ionize CBr bond. The carbocation is formed in the first step, which is preferred to be slowest step and RDS, and that water molecule is consuming this proton. So, it is losing proton to form alkene. Now, from the slowest step you can write down the rate determining step. From the rate determining step we can write rate is equal to K into concentration of tertiary butyl bromide, because only tertiary butyl bromide is participating in slowest step of the reaction. So, the rate of the reaction depends upon only concentration of the alkyl halide, hence it is considered as a first order reaction. Now, which alkyl halide is preferable for the E1 mechanism? Tertiary alkyl halide is preferred over secondary alkyl halide, which is preferred over primary alkyl halide. So, this forms a more stable carbocation than this one, this forms more stable carbocation than this one. So, any alkyl halide which forms more stable carbocation is a best substrate for E1 elimination. If more than one beta hydrogen is there, then there is always possibility for the formation of more than one alkene. The number of alkenes formed is equal to number of types of beta hydrogens present in the alkyl halide we have taken. I will consider this compound CH3, CH2, CH2, CHBr, CH3, CH2, CH2, CHBr, CH3. This is 2-bromopentane. This is say beta 1, this is say beta 2. Two types of beta hydrogens are there. When it is treated with alcoholic potassium hydroxide or a base, it provides C2H5O minus. Now it can consume either this proton from beta 1 carbon or beta 2 carbon. I will just show you those hydrogens separately for you. I will keep one hydrogen here. I will keep one hydrogen here. Now what will happen is, if ethoxide ion consumes this proton, you will get 2 pentene. If ethoxide ion consumes this proton, you will get 1 pentene. So two different products are possible: CH3, CH2, CH, double bond, CH3. This is 2 pentene. If this proton is consumed, CH3, CH2, CH2, CH double bond CH2, 1 pentene. If this proton is consumed, you are getting 2 pentene. If this proton is consumed, you are getting 1 pentene. Now the major product, which is major product, is important. This is the 2 pentene is the major product, which is more substituted alkene, and 1 pentene is minor product. So whenever more than one type of beta hydrogen is there during the dehydrohalogenation, dehydrohalogenation means removal of hydrogen and halogen from adjacent carbons, because it is beta elimination. So during dehydrohalogenation, whenever you have more than one type of beta hydrogen, which is the major product, is being decided by a rule called Sagejeff rule or Zaitsev rule. Actually the name is Zaitsev, but it is pronounced as Sagejeff. Sagejeff rule or Zaitsev rule states that during the dehydrohalogenation, the base preferably eliminates the proton from the beta carbon having less number of hydrogens to form more substituted alkene as major product. So this is the carbon which is having less number of hydrogens. It has 2 hydrogens, this has 3 hydrogens. So according to Sagejeff rule, poor becomes poorer. Poor carbon with respect to hydrogens will become further poorer. It is having 2 hydrogens, in the product it has only one product. So Sagejeff rule suggests that during the dehydrohalogenation of alkyl halide, when more than one type of beta hydrogen is there, the beta hydrogen from the carbon atom which has less number of carbon atoms is removed. That means poor becomes poorer. So as per that rule, Sagejeff rule or Zaitsev rule, 2 pentene is the major product and 1 pentene is the minor product, and this is called Sagejeff product. This is called Hofmann's product. Hofmann's product is formed when the carbon atom having more number of, when the beta carbon having more number of hydrogens is eliminated. So if the ethoxide ion removes the hydrogen from the beta carbon having more number of hydrogens, you will get a Hofmann's product. Hofmann's product is less stable product, less substituted alkene. Now let us see when Zaitsev product or Sagejeff product is feasible, when Hofmann's product is feasible. During even reactions or reactions following even mechanism, always Sagejeff product is major product. During the E2 reaction, in majority of cases, Sagejeff product is the major product, not Hofmann's product. Sagejeff product, here also Sagejeff product is major product during the majority cases. Only in few cases, the major product is Hofmann's product. Only in few instances, like when the leaving group is a poor leaving group like fluorine, when the base used is a bulky base. In such circumstances, I will give you few instances only. So in few instances, whenever the leaving group is poor leaving group, the base used is bulky group, then you will get Hofmann's product as a major product, whereas in all remaining cases, In E2 reactions, the major product is CH product. In all cases, invariably in even reactions, the major product is CH product or JEE product. I will show the few instances of what getting half months product here. I will give you when the leaving group is a poor leaving group like fluorine. I am taking CH3, CH2, CHF, CH3, 2-fluorobutane. When it is heated with alcoholic KOH, which provides base like C2H5O minus, which removes this proton beta carbon. This is beta 1 from beta 1 rather than from beta 2. Because CF bond is stronger, by the time CH bond is broken, CF bond is not completely removed. That is why some carbon ion character will be achieved to give carbon ion among these two carbons, which forms more stable carbon ion, obviously primary carbon ion. So that is why this hydrogen is preferentially eliminated. Now you will get CH3, CH2, CH double bond CH2, 1-butene is the major product, which is half month's product, because the hydrogen is eliminated from the beta carbon having more number of hydrogens. Then CH3, CH double bond CH, CH3, 2-butene, this is minor product, this is half month's product, this is CH product. Now this is one of the instances where half month's product is formed as major product, because fluorine is a poor leaving group. Now I will give you one more example for half month's product, that is when base is bulkier, bulky base is used. CH3, I will take another example, CH3, CH2, CH2, CHCl, CH3. This is one beta 1, this is beta 2. Here I am using potassium tertiary butoxide. This is a bulky base. Tertiary butoxide ion is a bulky base. This bulky base can eliminate the proton either from beta 1 or beta 2. Now since it is bulkier, it is easy for it to approach the terminal hydrogens rather than the internal hydrogens. Thereby you will get CH3, CH2, CH2. This proton is eliminated, preferably to give less substituted alkene. You will get CH3, CH2, CH2, CH double bond CH2, 1-pentene as major product, which is half month's product, plus the proton, if it is eliminated from beta 2, that is hindered carbon. This is hindered carbon. It is in between two bulky groups, so tertiary butoxide cannot approach this one. With a lot of difficulty, it can if it removes this proton, then you will get 2-pentene as a minor product. That is, CH product is minor product. Half month's product is less stable alkene, and CH product is more stable alkene. More stable alkene is minor product, less stable alkene is major product according to half month's rule.